Okay, good morning. Let's get started. We did a quick introduction to capacitance last time, but let's kind of start with a quick review there, and then we'll get more into it. We'll do another problem where we find the capacitance of a configuration that's a little different. Last time we did parallel plates, so this time we'll do something a little different. But just a quick review of capacitance. We've got some kind of setup here with two conductive surfaces, and oftentimes they're parallel plates, so we usually draw them that way, but it doesn't have to be. But they could be parallel plates. They could be a spherical shell around another spherical conductor. It could be a cylindrical conductor surrounded by a cylindrical shell. Could be any two conductors. So we've got these plates here. We hook up some kind of potential difference, a battery, a power supply, something like that. And what happens is that battery pulls an electron off of one plate, moves it around, and deposits it on the other plate. So if our battery has this orientation, or our power supply, oops, what am I doing? There we go. So it doesn't matter how you think of it. Pulls positives off of one plate, puts them on the other. Really, we know it's pulling electrons off of the left plate. So it pulls an electron off of that plate and it moves it around and puts it over here. And that leaves the lack of an electron or an excess positive charge on one plate. Now, that first electron is really easy to move, right? It's no problem at all. You don't do any work moving that first electron over. But the second electron, when you go to pull it off the positive plate, it's attracted to that positive charge. So you have to do a tiny bit of work pulling it away. And when you go to put it on the other plate, there's already one negative charge there. So you have to do a tiny bit of work pushing that second one on there because those two charges repel. So the first charge, no problem. It's easy to move over. The second charge, you do a tiny bit of work moving it around. Then you go to move the third charge. Now there's two positives attracting that electron when you go to pull the electron off the plate. And there's two negatives already on the plate you're trying to put the electron on, so they repel it. So you do a little bit more work, right? And you keep moving charges until your power supply or your battery can't move anymore. It's limited by its potential difference. It can't move any more charges, and it stops moving. So you end up with something like this. So if you plot the charge on that capacitor, this would be a positive on that plate and negative on that plate, right? Versus the potential difference on your power supply, you'd have some point here. Now you crank up the power supply a little bit, or you get a bigger battery, and it's able to move some more charges over. So it does. It moves a few more charges, and we get a data point that's up here maybe. And then we crank up the power supply some more, or put a bigger battery in, and more charges move. And we get a data point up here maybe. So what happens is we get a plot that looks something like this. As we increase the power supply voltage, the potential difference, we get more charge transferred from one plate to the other. So the slope of this line is what we're interested in. We know that the charge is proportional to the potential difference across the plates. And if we make that an equal sign, we throw a proportionality constant in there, we get this equation where that is the capacitance. And what does it depend on? It depends on the physical properties of the capacitor, right? The size of the plates, how close they are together, things like that, the shape of the plates, right? Is it a parallel plate? Is it spherical? Is it cylindrical? Those kinds of things. So this is, so that only depends on the capacitor. And it's the same, so it does not depend on the power supply. So the capacitor, it has a certain capacitance. It doesn't matter if it's hooked up to a battery and it has charge stored on it. It doesn't matter if it's sitting in a drawer somewhere. The capacitor has a certain capacitance. What does it depend on? The size of the plates, the spacing between the plates, the shape of it, things like that. Okay. Okay, so last time we did parallel plate capacitor, we found what the capacitance was. And we're going to do that again this time, but instead of doing parallel plates, we'll do concentric spherical conductors. So some kind of solid spherical conductor with a spherical shell around it. And remember the thought process. We are looking for, we're looking to replicate this equation, right? So can we find delta V in terms of charge, and then whatever is left over in that equation is going to be capacitance, right? That's what we're trying to figure out. So how do we get delta V? Well, we have an equation that's delta V in terms of the electric field. So we're going to start with that. So this is our problem. Okay. So we've got some inner conductor, we'll call that RA, and some outer conductor, RB. And we want to use this equation because what does the electric field usually depend on? Charge or charge density, right? And we can integrate that and get delta V, and that kind of points us in the right direction. We're trying to get delta V and Q in the same equation, and then we can figure out what C is from that. Okay. So first thing we need to know is what is the electric field between the plates there? Well, we could use Gauss's law. We could look at that. We should know by now what the electric field is between the plates. Because we have spherical symmetry, all the charge outside of our radius does not affect us, right? It cancels out if we have spherical symmetry. Only the charge inside of our radius matters. And what do we treat it like? A point charge at the origin, okay? Because we have spherical symmetry. So, or just go ahead and apply Gauss's law. Draw a Gaussian surface between these plates, and you end up with this equation. E is KQ over R squared. And one of these is going to have a plus Q on it, and the other one's going to have minus Q, right? Our electric field, I'll draw it here in green, is going to point this way. Okay. So we're going to say delta V minus the integral and we're moving from A to B. We'll go from A to B. So that means the dot product is going to give us a cosine of 0 degrees. And we're going from A to B, small number to big number, right? A is smaller than B. I think that's right, but let's check and see. So what do we, so this is going to be the voltage at B, the delta V. Well, actually, I don't care about the sign here. I just want to know the potential difference across these plates, right? So I don't really care about the sign. I know that the one that has the positive charge, the plate that has the positive charge is going to be at higher potential than the plate that has a negative charge, right? I know that. So all I care about is delta V. All right, so what do we end up with here? We end up with a KQ and an integral of 1 over R squared. And that gives us a, I'm dropping my minus signs because I don't care about them. 1 over R from RA to RB. Again, we've got, and so where do I end up with this? I end up with a RB, 1 over RB minus 1 over RA, right? I'm just going to make it positive. So so if I want to make it positive, then I have to flip these around, right? Because this is a negative number right here. So I'm going to flip them around to make it positive, and then I can eliminate the absolute value signs. Okay, so now I have delta V is equal to something times Q. So I just need to rearrange it to get it into my capacitor formula. So I'll rearrange that. I'll get Q all by itself on one side. And I'll get 1 over K times that times delta V. So what does this have to be? My capacitance. C must equal 1 over K times 1 over RA minus 1 over RB. What does it depend on? The size, right? The shape of the capacitor, and that's it. Okay, so we did one last time for parallel plate capacitors, and we got that it depended on the surface area and the distance between the plates. Here, we get that it depends on the radii of the two spheres. And if we did cylindrical ones, we would get a similar equation for that. Okay. So a capacitor, what does a capacitor do? Let's just go back and think about it for a second. A lot of people say a capacitor stores charge. Really, what it does is it stores charge separation, right? It stores energy. It took energy to separate those charges. Those negative charges, those electrons all pushed onto that one plate, they repel each other. They don't all want to be there. So we take this capacitor, we charge it up, we remove the battery, and we've got this energy stored there. Right, you got a capacitor, hook it up to a battery. Then you remove the battery. And we've got this stored energy. Because those charges, where can they go? When you remove the connection through the battery, those charges are stuck on the plates of that capacitor. They can't go anywhere. So they'll just stay like that. We've got this stored energy. And then maybe we'll hook that up later. We'll hook it up to a light bulb or something. So we'll hook this up to some other and we'll get current to flow, right? Current will flow. And it'll keep flowing until all the charges have gone back to their original place. There's no charge separation, and then there won't be any more current after that. So we can put energy in, we can do work on the capacitor, moving charges from one plate to the other, and that energy is stored there, kind of like compressing a spring and then leaving it compressed like that. That energy is stored there. And then we can take that at some later time, hook it up to a light bulb or some other device and get that energy back out of it.
I got a question, Professor.
Okay.
When you hook up a light bulb, will the electric potential between those two plates decrease when they
Yes. Yes, it will. So it'll be this curve. The question is, as it feeds energy into the light bulb, does the potential across the capacitor decrease? Yes. So it will. So as it's like doing this curve in reverse, right? So as we increased the voltage, we got more charge stored, right? Well, if we hook the charged capacitor up to a light bulb, as the charge bleeds out, what's going to happen? We're going to be going down this way, and so the voltage across the capacitor is going to get smaller and smaller. Yeah.
Thank you. So the light bulb grows darker and darker.
Yes, yeah. It will not supply a consistent current. The current will be big at first, and then it'll start to get smaller and smaller as the potential difference gets smaller and smaller.
Thank you.
Actually, that's your lab this week. So one thing we tend to do when we think about capacitors is that we kind of, in our mind, we hook them up to a battery and boom, magically, they instantaneously charge up to some value. That's not how it works. It takes some time to move the electrons around to the other side. Now, those times are usually short, right? They're usually milliseconds or something, but it does take some time. So if I take a capacitor and I hook it up to something, usually there's some resistance in the circuit. Maybe it's a light bulb, maybe it's something else. But if I have a capacitor and I have a resistor and I have my battery, let me put a switch in here too. Hold on. So when I close that switch, it doesn't magically become charged. The current has to flow and charge that capacitor. And when I say current flows, it flows everywhere except for, where does it not flow? Right here, right? That capacitor is an open circuit. There's no way for the charge to get across it. If there was, it wouldn't be a capacitor anymore, right? It's an open circuit. So what do we do? When we say that the current flows in this circuit, it flows everywhere because that capacitor is like a reservoir. And current can flow until that reservoir gets filled up, and then current stops flowing, right? Think about, like, I don't know, a big bucket and water being pumped around, okay? So water can be pumped everywhere as long as that big bucket can keep taking more and more water. As soon as it fills up, the water stops flowing everywhere else in the hoses and stuff in the circuit, right? So it takes a little bit of time to charge up. If this is time and this is the charge or voltage on the capacitor, it takes a little bit of time to charge up, and that's the maximum. It's actually, it's an exponential. And discharging is the same thing. It takes time to discharge. So you have a fully charged capacitor. You want to hook up a light bulb or some other resistor there. You close the switch, and at first, what happens? You get a nice big current flowing, and it decays over time and eventually goes to zero as t goes to infinity. So this could be Q or current. Okay. Anyway, more on that in lab this week. Yeah, the times are short. The times are typically short. So, milliseconds, things like that for this to occur. So, you don't notice it. It seems instantaneous because the times are relatively short, but it doesn't have to be short. It could be long. What does it depend on? What two things would it depend on? How fast this capacitor charges up and how fast it discharges? It depends on the capacitance. Yes, if the capacitance is big, it can store lots and lots of charge, right? So it would take longer to charge it up, and it would take longer for it to discharge. And what else does it depend on? The current, which is R, right? So if you put a big resistor in the circuit, it takes longer to charge up the capacitor because you're fighting that resistor. If you have a small resistance in the circuit, it charges up relatively quickly. So those are the two things that this depends on, and that's the lab. Okay. All right. So what we like to do, or it's not so much we like to do it, but it's a necessity. Oftentimes you have to hook up more than one capacitor in a circuit for a variety of reasons. Maybe you look in your drawer and you don't have the right size capacitor you need, and so you have to use two to make the one you need. Maybe there's some other reason, but we often have multiple capacitors in a circuit. And so there are two main ways we can hook them up: series and parallel. Yes, this is exactly like equivalent resistance. But first we're going to do capacitors and learn about those, because we're just coming off of potential, right? electric potential chapter, and capacitors, parallel plate capacitors, the electric field, the potential difference between the plates, it just falls in so nicely after that chapter. We're going to learn that first. Then we'll talk about current and resistance later, although you've already had your lab on it, so you know about that already. So combinations of capacitors, series and parallel. I'll just draw two. So here's my source of potential difference, my battery or DC power supply, and I can have two capacitors there. And in parallel, they would look more like this. And remember, we've got our DC power supply. Usually I draw it like this, but you just have to be careful because if you get a little sloppy, this starts to look an awful lot like that. And one of those is a capacitor and one of those is a battery. So you have to be careful when you only draw it with one segment like that. Our capacitor, of course, is parallel plates like most capacitors, a lot of capacitors are. And our resistor, okay. All right, so let's talk about parallel for a second because capacitors are a little different, right? This is not gonna, we're not gonna end up with the same formulas for capacitors that we had for our resistors. Start with parallel. So when we think about these parallel paths, right, to the other side, I think it's easier to think a little bit in terms of series and parallel with resistors and current flowing. And knowing that when current flows through a circuit, if all the current that goes through the first device has to go through the second device, there are no branches, no forks in the road, all the current that goes through the first has to go through the second, they are in series with each other. And if we can get from point A to point B through two different paths, those two paths are in parallel with each other. So in this case, we can get from point A to point B, excuse me, through two different paths, right? Through this path or through this path. These are parallel paths to the other side. And if you think about this, one side of those plates is at one potential, electric potential, and the other side is at another electric potential. And so as we add charges, as this battery moves charges around from one plate to the other, what does it look like? It looks like one big plate, right? Because they're connected together. So the left plates here are connected together, and the right plates are connected together. It's as if we have one big plate on each side. So for as far as capacitance is concerned, I'll clean this up later. Or muck it up, one or the other. As far as capacitance is concerned, we can treat them like one big plate. So C equivalent for this circuit is C1 plus C2. And if I had more, I would just add them up. And of course, we know voltage is the same. Because they're connected electrically to each other. It doesn't matter, if I have a plate, here and a plate here, and I connect them with a wire, as the battery tries to push whatever it is, electrons onto that plate, the electrons say, oh, wait a minute, there's another plate that's connected here. As far as those electrons are concerned, it's one big plate. So they'll spread out. One of them will go way over here to get away from the others, right? And they'll just spread out because they're electrically connected. As far as the electrons are concerned, it's one big plate. Series. So this one's a little trickier. Let's go back up to parallel for a second. So we need, let me write it this way. Let me, instead of words, let's just put an equation here. We got okay. And what about charge? The charge on in the whole system is just the sum of the charge on the two individual capacitors. The voltage across every device is the same, and the equivalent capacitance, we add up the capacitors. So you can already see this is different than resistors, right? With resistors, we had the 1 over R equivalent is 1 over R1 plus 1 over R2. So capacitors in parallel add like resistors did in series. Okay, so it's a little different. Okay, now for series. Let's think about what's going on here. The battery moves a charge. Where does the charge come from? The leftmost plate. An electron comes off of this plate, leaving a positive behind. Where does it go? It goes over here on the rightmost plate, right? This is an open circuit there. We can't cross that boundary, right? That's an open circuit. Nothing, no connection there, no electrical connection. But what happens when we move that electron around? It creates some electric fields and forces. And what happens to this intersection here? Charges redistribute, right? An electron from over here gets repelled and moves to the other side. So we end up with an electron over here and a positive over here. because of the forces involved from the charges that moved around the outside, okay? Now what happens, the battery moves another charge around. The battery plucks an electron off of that plate and sticks it over here. And that creates a little bit of an electric field, and it forces the charges to move internally here. So this area in here, this area in here is electrically isolated, right? And these guys are just redistributing. And so we get another minus and plus. And we keep doing that. The battery moves a couple of more charges over, and internally here, a couple of more charges shift. So it doesn't matter what size these capacitors are. If this is C1 over here, and this is C2, and C2 is twice as big as C1, it doesn't matter. They both have the same charge stored on them because the battery only sees the outside two plates. So if it pulls 4 coulombs of charge off of this plate, it has to put 4 coulombs onto this plate. And then internally, within that gray box, internally, charges redistribute until there are no more forces on them causing them to move. So the plates would have the same charge as the outer plates. So it doesn't matter if I have 2 capacitors or 10 capacitors in series, they all have the same charge stored in them because the battery does the outside 2 plates and all the internal plates align with them, match them. So in series, the charge on every capacitor is the same.
Professor, just to confirm one more time, it doesn't even matter like if the area of one capacitor is bigger than the other.
It doesn't matter. When they're hooked
Even
up
if
in
it's a
series,
huge capacitor. Okay.
this is what you get. And what is it equal to? Q total.
So it depends on the smaller capacitor.
Which one limits you here? We'll have to think about that. It depends on the
I think it depends on the smaller one.
yeah, but what it depends on is how the voltage ends up splitting, right? How much voltage there is, the equivalent capacitance, things like that. So I think it's more heavily influenced by the smaller capacitor. I think you're right. Okay, question here. Why is that the total charge? So everyone, let's say every one of these capacitors is storing 5 microcoulombs of charge. C1 has 5 microcoulombs, C2 has 5 microcoulombs. Why is it that the total is only 5, not 10? Well, what would happen if I took this thing and I hooked it up to a battery? So I hooked it up to a light bulb. So I've got it here like this. I charge it up. Let me just draw it out for you. So we've got 2, let's just make it 2 capacitors. We've got a battery. We charge them up, right? So we end up with Q1 and Q2. I'm just going to call them Q because we know they're the same, right? Q charged on each one. But how much charge went through the battery while we were doing that? only Q. The other, the other one was just internal within the capacitors, charges redistributing themselves. So what happens if we remove the battery? And then we hook up a light bulb or something. How much charge is going to go through the light bulb? Only Q, right? Whatever went through the battery. So what went through the battery over here? The red ones went through the battery. The green ones just redistributed internally. Oops, I made too many. That's okay. I can fix that. So what's going to go through the battery here were the 4 red charges, right? And then over here, what are we going to get out through this? Just the red charges. And what's going to happen here? The green ones will just redistribute internally. So that's why this is the tricky part. You could have 10 capacitors in series, each one storing 5 microcoulombs of charge. How much do you have stored in the system? Just 5. Just 5. Whatever that is on one capacitor. So the charge is the same on everything. So up here, the voltage was the same on everything in parallel. Down here in series, the charge is the same on all of them. And the voltages, of course, add up. Where are we here? Let me sneak in the obvious ones, maybe. Right, the voltages add up, the charges are the same, and now we need our equivalent capacitor. Because of this weird thing with the charges, you can see the capacitance doesn't go up when we add more capacitors. The total capacitance actually goes down. So this is sort of like resistors in parallel, right? The more resistors we add in parallel, the lower the resistance was. So these add the way resistors added in parallel. So 1 over C equivalent is 1 over C1 plus 1 over C2 plus ... And you can derive these very quickly. Let me do one for you. We start with Q equals CV. And we say Q1, charge on capacitor 1 in our series circuit, is C1 times the voltage across that capacitor. And Q2 is its capacitance times its voltage. And what else do we know? We know that Q1 is equal to Q2 is equal to, I'm just going to call it Q from now on instead of 1 and 2. And I know that the delta V across 1, I should really put deltas in here, sorry about that. Delta V across 1 plus the delta V across 2 is delta V on the battery. And so if I take this equation for voltage, then what is V1? V1 is just Q1 over C1, right? And what is V2? It's Q2 over C2. And that's going to equal delta V battery. And the Q's are the same, so I don't need subscripts there. So I can carry it out. Q 1 over C1 plus 1 over C2 And we know that Q is equal to CV, right? Q equals CV. So this is Q total. And so this thing in here must be C equivalent, right? You can do the same thing with parallel capacitors. You can do the same thing with series and parallel resistors. You can derive the R equivalent very simply by starting with the equations, right? So we know for a resistor, you would start with V equals IR. And then for a capacitor, you start with Q equals CV. Then you pick the formulas that are correct for whatever you're trying to prove, series or parallel. And then you go from there and make some substitutions, and you very quickly can get the equivalent resistance or equivalent capacitance. Okay, so let's practice a couple. Question about this one more time. The charge on the internal is just redistributed, right? The battery can't affect anything beyond these two plates here, this one and this one. The battery is just moving charges between those two plates. So the battery is doing a certain amount of work, moving a certain amount of charges from the leftmost plate to the rightmost plate. And all the stuff internally is just moving. As the battery moves a charge around, internally, even though this capacitor is these two plates and this capacitor is these two plates, the internal ones are kind of become one system and the external ones become one system. So the battery is moving charges between the external plates, the internal plates, the charges are just moving to match them. So as you bleed the charges off of those external plates, what are the internal ones doing? They're just bleeding back internally. You're not getting them out through the light bulb or whatever device you're trying to power. Okay, let's take a look at a few examples here. Got a battery, capacitor. Make it C and 2C. Tell me the equivalent capacitance. Okay, they're in series, so it's just the opposite of resistors. In series, the capacitance adds this way. 1 over C1 plus 1 over C2 is 1 over C equivalent. And of course, what happens if I do this? Nothing happens, right? Because these wires in our circuit diagrams are all zero resistance wires. It doesn't matter how long they are, how many bends they take. It doesn't matter. All right, and this one. So it's really tempting. I know when you look at this, it kind of looks like they're in parallel. Don't fall for that trap. Think about the current path, okay? I know we draw parallel like this, right? But in this case, they might look like that, but think about the current path. The current goes through, if the current could go through these capacitors, it would go through one, and then it would go through the other one. There are no forks in the road. There are no branches for it to split off and take another path. These are in series. Okay. All right, why don't we take a 10-minute break, and then we'll come back to series and parallel capacitors. All right, we're back. So what we want to do is use our rules for series and parallel capacitors to solve more complicated circuits. So let's take a look at, start making these a little more interesting. Let's do this circuit. All right, so what's the thought process on this one? These three cannot be combined straight up, right? They're not, all three are not in parallel, all three are not in series. But if you look carefully, you can see that two of them are in parallel. Just look for something you can, some little chunk you can bite off and solve, right? So take a look at this right here. You've got these two guys are parallel. So we're going to call that C equivalent 1. And because they're in parallel, we can just add them up, right? So I can redraw this circuit now. This one I haven't dealt with yet. I've combined these two into one equivalent resistor, calling that C equivalent 1. And I know that's equal to 2C. Now I say, okay, that was one little chunk I could deal with. I did it. Now I look at the circuit again and I say, oh, I have two in series. So I say my C equivalent 2 so that's 1 over 2C plus 1 over 2C is 2 over 2C, or just C. Don't forget at the end to take the reciprocal. So I could redraw this circuit if I wanted to as one equivalent resistor. So the technique is you can have a very complicated cluster, very complicated circuit with capacitors or resistors, but we're doing capacitors now, and reduce it down to one equivalent capacitor and solve for whatever, the charge, the voltage, things like that. And then you start working backwards and filling things in, working backwards, filling things in. And eventually you can work it all the way down to 1 and then all the way back and know the charge and delta V on every capacitor in your circuit. That's the technique. All right, so let's do this one. We'll add another capacitor or two. Okay, we'll make these 3, this C, that 2C. Okay, so see if you can do this one. Okay, you're spotting something you can do right away, because you can't combine all 5 of these right off the bat. You've got to look and see what you notice here. So one thing you notice is that these 3 are in series. So we'll call that C equivalent 1. Okay, so I can redraw this circuit now. I've got my battery is still the same. My 2C capacitor I haven't messed with yet. This capacitor I haven't done anything with yet. They're the same, but those 3 now become 1. Now it looks just like the one we did earlier, right? So we have 2 in parallel. And we're going to call that C equivalent 2. And that's just a C plus C. And then you draw it out as 1. Right? And this is okay. C equivalent 3. Good. Should we put some numbers in one of these? Yes, we should. So we're going to call this Q1, Q2, and Q3. We're going to try to find the charge on every capacitor and the voltage on every capacitor. And we'll let the capacitance be 1 farad. So capacitance, the units for capacitance are farads, and it's a very large unit of capacitance. So most of the time when you're grabbing capacitors out of your drawer, they're nanofarads, microfarads, picofarads. They're really small. A 1 farad capacitor is really, really big. Now, one of the things that is really hot right now in engineering is trying to develop high capacitance capacitors. They call them super capacitors or ultra capacitors. And the reason is that a capacitor acts a lot like a battery, but batteries are a pain in the neck, right? They take a long time to charge because you have to reverse a chemical reaction inside the battery. They take a long time to charge. Batteries lose their ability to hold, every time they're recharged, they don't quite charge back. The materials don't deposit exactly the same way internal to the battery. So you keep recharging it and your capacity goes down over time. They're a pain. There's lots of chemicals in there, and that has to be disposed of when the battery life has ended, right? So batteries are a pain. Capacitors, if you could, instead of having a battery in your phone and charging your phone for an hour, you had a capacitor in there that you could plug in for 10 seconds, that would be kind of nice, right? If you could get enough charge in there in a very short amount of time, that capacitor would charge up very quickly. And if you could run it all day on the capacitor, that would be nice. Now, we've talked about this already. Capacitors don't maintain a constant potential difference, right? So you'd have to figure something out to deal with that. Maybe you would need more capacitors than you have battery, just so you could only use part of it, right? And then recharge it and use part of it. But it's a big topic right now, trying to create these capacitors, because it would, the applications are really out there. One application is for regenerative braking in cars. When you hit your brakes in your car, it hooks up a generator and it charges a battery or some capacitor bank. And the reason why they like the capacitor bank is that you have a very short time window, right? When you're braking, you have a few seconds, you're charging, and you might not be able to get much charge into a battery. Some cars do use batteries, most of them do, but some of them now are supplementing the batteries with ultra capacitors or super capacitors, because you can charge them much faster. You can store that charge very quickly. And then when you start up from the red light, you can get that energy back out and get your car moving, harness some of that energy of motion. And how do they develop these ultra capacitors, these super capacitors? You need tons of surface area, right? We've already seen that the capacitance depends on the surface area, storing charge. Well, what's one of the hot topics now in science? Nanotechnology, right? Nanotube structures, nano this, nano that. Well, when they create these nanotube structures, there are lots of little tubes and things in there. What does that mean? There's tons of surface area. And so they're using this nanotechnology to create these structures with nanotubes in them and use those as capacitors and storing tons and tons of charge. And so they're coming up with these very high capacitive capacitors. So Google ultra capacitor or super capacitor, you'll see some of those applications. All right. So if C is 1 farad, just to keep the math easy here, even though it's not as realistic, it's probably 1 microfarad, would be more typical, but that's okay. This we can do in our head this way. So we'll use these two values. Your job is to find delta V and Q for each capacitor. Okay. go for it. So the first step is to get this down to one equivalent capacitor and figure out what Q and delta V are for that one equivalent capacitor. And then start stepping backwards and figuring things out as you go. That's the unit. Question, what is F? This is the unit for capacitance, the farad, the unit for capacitance. There you go. So we already got this earlier. We got this down to one equivalent capacitor, so I won't do that again. Okay, I've got two different C's here. One, oftentimes in the book, when you see circuit problems and there's a capacitance there, they'll just write them the way I am, C, 2C, 3C, meaning the value of the capacitance. So this is the capacitance. But C is also our symbol for the unit for charge, right? The Coulomb. So here we have our unit for charge, 6 coulombs of charge. Okay, so what's the next step? We have to work backwards. So we went from here, we went to something like this, right? Had that 2C capacitor and this other equivalent capacitor that was also 2C, right? So the key here is charge. Now you want to be looking at charge. So you know on this one, Q was 6 coulombs. So that is not really a capacitor. That is really a combination of two capacitors in series. So if the total charge on that system of capacitors is 6 coulombs, what has to be on each of the individual ones in series? 6 coulombs. So we're going to call this Q1 and this Q23. Now we can figure out the potential difference across each one because we know Q equals CV. And we know this, the capacitance, and we know the charge. In this case, we knew it had to be the same because the two capacitors are the same. We had a 2C here and a 2C here. So because they had the same capacitance and there's only two of them in series, the 6 volts from our power supply, oops, what happened? Uh-oh. I hate when it does that. Okay, we're back. The 6 volts from our power supply gets split equally over those two capacitors. If the capacitance values were different, if one of these, if this was a 3C instead of a 2C, then the voltages would not be the same, and you'd have to do these calculations to figure out what the voltages are. In this case, it was straightforward because they were the same. Okay, so now we can step back. We have one more step back. We haven't figured out all the values yet. We have to go one more. So we go one more step backwards, and that brings us to our original circuit. What was it? Yeah. And we can fill these in with what we know. No, Q2. So these are in this capacitor is really two in parallel. So delta V has to be the same for those, right? So delta V1 has to equal delta, not 1, delta V2 has to equal delta V3 has to equal delta V23, which is 3 volts, right? And then I can figure out the charge on each one because I know the voltage and the capacitance. So Q2 is C2 delta V2. Six coulombs. Is that right? No, it's one. Sorry, it's one coulomb. Sorry, 1 farad times 3 volts is 3 coulombs. And the other one also is going to have 3 coulombs, and 3 makes 6, which is what is in the combined. So think about whether they add up properly. These two are in parallel, so the charge Q adds together to give you your total charge. And it seems to check out. So we've got everything. We've got delta V, and we've got Q for each of these capacitors. You can see this is a fairly powerful technique. You can do a very complicated system. Okay, so let's think about parallel plate capacitors a little bit. If we have a, let's just do a conductive conductive plate or sheet of charge. Usually in physics books, they use plate for conductors and sheet for insulators. So we've got this large conductive plate, right? Just basically a two-dimensional object. But of course, with a conductor, there's always some thickness to that plate. That's what I've drawn here. And it's going to go off like that. Okay, so what happens as we add charge to this plate? Some of it will stay on one surface and some will go to the other surface because it's a conductor. Charges are free to move. They'll go wherever they want. So we start to add some charge here. And what happens, some of it, half of it, will immediately go to the opposite surface. So it's hard for me to draw like this. Let's just do like that. Okay. So for a conductor, sigma is charge per area. So we would look at this, just the charge on this side and the area on this side to get sigma, or just the charge on this side and the area on that side to get sigma, right? We wouldn't combine them and use both sides. So sigma is defined a little differently. It's not really, but it comes out a little differently. With an insulator, the charge stays wherever you put it. So usually when you put charge on the face of an insulator, you put it all on one side, and then that's your sigma, charge and area. You don't have to worry about half of it moving to another surface. So when we use this to get E, we know the electric field is going to come off in both directions, right? We would draw a Gaussian surface. And one way to draw the Gaussian surface is to put one surface inside that conductor. That's not a very good cylinder, is it? That's one way to draw it. Another way to draw it would be like this. That would be okay also. Either way gives you the same answer. what do we get for our electric field? Sigma over epsilon naught. And we get that because the charge splits. Half is on one face of that conductor, half is on the other face of the conductor. With an insulator, all the charge is on one face, so the formula ends up being a little different. But if you put the same amount of charge on a conductor and the same amount on an insulator, you get the exact same electric field. Okay, hopefully that was some review. Now, let's take our conductive plate and let's bring another conductive plate close by. So we have our conductive plate. And we're bringing in another conductive plate that has negative charge on it. Okay, so the question here is, it says a second plate with the same magnitude charge as the first, but opposite sign is now held near the first. The plates are large and close. So which diagram best shows the various distributions of charge on the two plates? Where is that charge going to end up? Does it stay where it is? Does it move? So let's think about this for a second. We've got one plate and it's got some charge on it, right? Half on one side, half on the other side. Now we bring another plate close by. With the equal amount of negative charge. And some of those positives and some of those negatives are attracted to each other. And so we end up with something like this. We end up with something like this. And then we make those plates a little bit bigger, a little bit longer. Let's, right now they're kind of small. Let's make them taller. Let's stretch them out a little bit. So the plates, we've stretched the plates out a little bit. And more charges move around to the other side. And so we end up with something like this. More charges move around. And then we stretch those plates so they're infinitely long. And all the charge moves around and is on the innermost surface. 2, 3, 4, 5, 6, 7, 8. Okay. And the sigma out here is 0. I get the charges would spread out more, yes. They'd space out more. Okay, so as those plates become infinitely large, all the charges end up on the innermost surface. And so let's take a look at this next example. So we've got our two very large plates close together. So for all purposes, would treat them like infinitely large plates. And that's really not, I think I've mentioned before, it's really not a bad assumption for most capacitors, because what do you want in a capacitor? You want to be able to store charge. So the plate area is fairly large, and you want it in a small package, and most of them the plates are very close together. So the plates, because the spacing is so small compared to the size of the plates, it looks like an infinite plate. You know, most of the volume inside that capacitor, it looks like it's infinitely large. All right, so here's our situation. We've got these two large conducting plates, a distance d apart, and you are going to we know that the charges all attract to the innermost surfaces, right? You're going to draw a vector to represent the electric field at each one of these points, 1, 2, 3, and 4. So the electric field at each point. So let's start with 1 and 4. What happens outside of these plates? The electric field is 0, that's right. If you go back to this drawing, sigma was 0 there, right? So that means that E is 0 outside. And what is it in between? It's nice and uniform, constant. Same everywhere in there, right? So here, E is 0. And what do we get in between? A nice uniform electric field pointing from the positive plate to the negative plate. So I'll draw a vector, same size vector at each. Are those the same? Yeah, close enough. Okay. So we have E, here it says write an expression for the electric field at each point. And what is the electric field equal to? Yes. Sigma over epsilon naught. In this case, they're calling it sigma naught, I guess so. Okay. How do you get that? You draw a Gaussian, I would draw it right inside the surface like that. And then you say the integral E dot dA is Q in over epsilon naught. And that integral could be over the left side of our cylinder and over the curved side of our cylinder and over the right side of our cylinder. And that has to equal Q in over epsilon naught. And of course, the left side is 0 because it's inside of a conductor. There's no electric field there. And the curved surface is 0 because the electric field is parallel. It doesn't penetrate the surface at all, right? The flux through the surface is 0. So we only get this. So we have EA is Q in over epsilon naught. What is Q in? It's sigma A. So E is sigma over epsilon naught. That's an epsilon naught. The A's cancel. Okay. Now, where are we? Potential. So find the potential difference between the plates. Because our electric field is uniform, it's constant, it comes out of the integral, and we just get E times the integral of ds, which is the distance between the plates. And so in this case, what is that? It's sigma d over epsilon naught, if we're putting it in those terms, right? Okay, so let's do this. We've got these two plates. They're charged up. They are isolated from one another, no connections between them. And we're taking the one and pushing it closer to the other one. So we're reducing the distance between the plates. The right plate is moved to the left, closer to the left plate. They are insulated, isolated. So what happens to the charge density on each plate? What happens to the electric fields inside and outside? What happens to the potential difference between the plates? Do they stay the same? Do they change? How do they change? Smaller, bigger? Start with the first one, charge density. Okay, charge density remains the same. Why does it remain the same? Because these plates are insulated, right? They are isolated from each other, from everything else. The charge can't go anywhere and it can't get any new charge. They are isolated. So when you move them around, can't get any more charge, right? Can't lose it. So Q has to stay the same. The area of the plate's not changing. Sigma stays the same. Okay. So what happens to the electric field between the plates? What does the electric field depend on? Sigma. What happened to sigma? Stayed the same. Okay. Does that make sense from what we know about electric fields near infinite sheets? Yes. Does the electric field change as you move away from an infinite sheet or near an infinite sheet? No, it's uniform. It's the same everywhere. So what difference does it make if the sheets are here or here or here? If the field is the same everywhere, it's the same everywhere, right? It doesn't matter how far apart they are. So it makes sense. And delta V. Delta V, what happens to delta V? Delta V is E times the distance, right? So if the distance gets smaller and E stays the same, then delta V has to get smaller. Okay. Now, what are we going to do? You know me, I can't leave it at that. Now, we're going to leave our plates hooked up to the battery. Okay, so we've got these two plates. We've got a battery hooked up at separated charges, and we're going to leave them hooked up to that battery. And we are going to move, what does this say? Here we are. And we are going to move the one plate closer to the other one, but this time we'll leave them connected to the battery. So what happens to these three things? The potential difference, the charge density, and the electric field. Let's do the potential difference first. What happens to delta V?
Delta V stays the same.
Delta V stays the same because it's hooked up to a constant potential source. That's what a battery is, right? It strives to maintain a constant potential difference. So the battery is going to move charges. There's actually a path for charges to flow between the plates because it's hooked up through the battery. The battery is going to move charges until the potential difference between those plates is just right, whatever voltage it's trying to maintain. So delta V stays the same. So what's going to happen to our electric field? What happens to the electric field? Delta V stays the same. D gets smaller. So how can delta V stay the same if D gets smaller? E has to increase. Okay, what happens to sigma? What does E depend on? E only depends on one thing, sigma. So if E got bigger, what happened to sigma? It got bigger. Okay. This is a very typical end of chapter problem. You'll see this in your textbook. It asks you if you have a parallel plate capacitor that's charged up and you leave it connected to the battery and move the plates or insert a dielectric or do something to it, what happens to the electric field, the charge density, and the potential difference? And then they ask you the same question again, but this time it's disconnected from the battery and you do whatever, you insert a dielectric or move the plates or something, what happens to the electric field, the charge density, and the potential difference? Very common problem. All right, so this is a good stopping point, and we are out of time, so it's a good stopping point. I'll stop the video. We've got a lab lecture coming up. The lab's posted. RC time constant. So some of the stuff we're talking about now, we're getting closer to being aligned again with our lab and lecture.